Topics in Post-Harvest Technology. Calculating Refrigeration Load, Part 1. Removing sensible heat during cooling. Refrigeration load in the U.S. is calculated as tons of refrigeration. A ton of refrigeration is based on BTUs. A BTU, or British thermal unit, is defined as the amount of heat it takes to raise 1 pound of liquid water 1 degree Fahrenheit. Conversely, a BTU could be thought of as the amount of heat to be absorbed lower 1 pound of liquid water 1 degree Fahrenheit. A ton of refrigeration is defined as the amount of heat absorbed by 1 ton of ice melting completely at 32 degrees within 24 hours. Since the melting ice is undergoing a phase change from solid to liquid, it requires much more energy to do this than simply raising the temperature of liquid water. It requires 144 BTUs to melt 1 pound of ice at 32 degrees. This value is known as the heat of fusion for water. Since the ton of ice must be melted in 24 hours, a ton of refrigeration absorbs 288,000 BTUs in 24 hours. Think of 2,000 pounds of ice times 144 BTUs per pound. This is equivalent to 12,000 BTUs per hour. Though a ton of refrigeration seems to indicate weight, it is actually an indicator of the heat absorbing ability of a system. The refrigeration requirement of any storage facility must be based on peak refrigeration load. The peak refrigeration load depends on the amount of commodity received each day, the temperature of the commodity at the time the cooling is initiated, the final temperature of the commodity after cooling, the speed of cooling required, and the specific heat of the commodity. Please note that a symbol for heat or energy is the triangle. Specific heat is equal to the energy needed to raise the temperature of a product X degrees divided by the energy required to raise the same weight of water the same number of degrees. It's called specific because it's relating everything to water. There is a formula for specific heat, and it is 0.008 times the percent water in the product plus 0.2. If you look up the percent water in cabbage, it is 92.4% on average. When we plug that value into the formula, we don't plug in the percentage symbol, we simply plug in the number. So now we have 0.008 times 92.4 plus 0.2, and this yields a specific heat for cabbage of 0.94. So to cool 1 pound of cabbage 1 degree Fahrenheit, we'd have to remove 0.94 BTUs of heat energy. To cool 1 pound of water 1 degree Fahrenheit, we'd have to remove 1 BTU of heat energy. The higher the water content of a commodity, the higher its specific heat, but all horticultural products cool faster than pure water as they all have specific heats less than 1. Problem. How much refrigeration is needed to cool 100 tons of cabbage to 32 degrees Fahrenheit within 12 hours when it is initially harvested at a temperature of 80 degrees Fahrenheit? There are 2 considerations: sensible heat and respiratory heat. Sensible heat is the amount of heat in the product due to the sun. So, sensible heat is equal to the pounds of produce to be cooled times the specific heat of the product times the temperature difference between the product's initial and final storage temperatures. For this problem, the initial temperature of the cabbage is 80 degrees Fahrenheit, and the final temperature will be 32 degrees Fahrenheit. That difference is 48 degrees Fahrenheit. The weight of the cabbage is 100 tons, or 2,000 pounds per ton times 100 tons is equal to 200,000 pounds. We calculated that the specific heat of cabbage is 0.94. So, using the sensible heat formula, the quantity of heat to be removed is 200,000 pounds times 0.94 times 48 degrees will yield 9,024,000 BTUs to be removed. This is the total amount of heat in the product due to the sun. Remember, a BTU is the amount of energy required to raise 1 pound of water 1 degree Fahrenheit. If this were water, since its specific heat is 1, the sensible heat to be removed would simply be 200,000 pounds times 48 degrees is equal to 9,600,000 BTUs. To cool the cabbage in 12 hours, only considering sensible heat and not also considering respiratory heat, we're going to take the value of 9,024,000 BTUs for the 100 tons of cabbage and divide it by 12 hours. We'll therefore need to remove 752,000 BTUs of heat energy per hour from the cabbage to cool it to 32 degrees in 12 hours. For a ton of refrigeration, by definition, 12,000 BTUs of heat are removed per hour. So we're going to take 752,000 BTUs per hour for the cabbage, and we're going to divide that by 12,000 BTUs per hour per ton of refrigeration. This yields a value of 63 tons of refrigeration needed to remove the sensible heat within 12 hours. If we were to cool the cabbage from 80 to 32 degrees Fahrenheit in 24 hours instead of 12 hours, or 1/2 as quickly, the refrigeration load also would be halved, so only a capacity of 31.5 tons of refrigeration would be required to remove the sensible heat. Likewise, if we were to remove the sensible heat from the cabbage in 6 instead of 12 hours, or twice as fast, we would need twice the refrigeration capacity, or 126 tons of refrigeration capacity. Summary points. A British thermal unit is defined as the amount of heat needed to raise 1 pound of water 1 degree Fahrenheit. A ton of refrigeration is a unit that indicates heat absorbing ability over a 24-hour period and is equivalent to 288,000 BTUs. Specific heat relates the amount of heat needed to raise the temperature of a commodity 1 degree Fahrenheit to the amount of heat needed to raise the same weight of water 1 degree Fahrenheit. When determining refrigeration load, one must consider the amount of product to be cooled, its initial temperature, its final temperature after cooling, the speed of cooling desired, and the specific heat of the commodity. When calculating refrigeration load, one must distinguish between sensible heat due to the sun and respiratory heat, which is also known as vital heat.